All right, I have one more example for you for multivariable linear systems, and it goes with that same idea. Let's try to get it in the row echelon form, and let's try to get back substitution. Some would say this problem looks a little bit easier because really, when I look at this system, I want to get a 0 here, and there's already a 0 here. So really, my top two equations are not changing. We have y minus z equals 0. And now the goal is to get 0 here. The way I would do that, I'd take the top equation and add the bottom equation. I don't even need to multiply the top equation by anything because x and negative x is going to add to 0. I would go into the middle, I add y and 2y. That's going to be 3y. Negative 3z and nothing is going to be negative 3z because we're adding. And 1 and negative 1, or negative 1 and 1, is 0. Good. So I got the 0 that I wanted. I got the 0 here. The last step to row echelon form is trying to get a 0 here. And it's a little bit, the work that needs to happen is, okay, I need to multiply this middle equation. All right, what can I multiply it by to cancel out the 3y? So the answer to that is I need to multiply everything in the middle equation by negative 3, and then add that result to the bottom, and I should be able to come up with some sort of an answer. Okay, so again, top equation, not changing. Middle equation, also not changing. Minus z equals 0. Here's where, in my head, I'm multiplying negative 3 times y. That's negative 3y. I add it to the bottom. I get the 0 that I want. Negative 3 times negative z, that's positive 3z. I add positive 3. So similar to the last problem, I'm getting all my variables to cancel out again. Negative 3 times 0 plus 0 is 0. Okay, just like in section 7.2, I have a different conclusion here. This bottom statement is true. So there are many solutions to this problem, but I'd like a way to algebraically express them. So if I look at this top equation, this middle equation here, if I was to add z to both sides, I could conclude that no matter what the answer to this problem is, or what the solutions are, y always has to be the same number as z. So I could actually do a substitution, because now I know that y has to be the same value as z. I could set up, if I go to the top equation here, I could actually do a replacement. I could say x plus y minus, instead of writing z, I'm going to write 3y equals negative 1. And here's the conclusion I could make. If I was to solve this for x, I would have x minus 2y equals negative 1. So x is equal to 2y minus 1. Okay, so while this is all good information, here's how I'm going to come up with my answer. All right, I'm going to say, all right, z and y, we can call them really any number we want, any variable, but they're the same. If x is, if z is a, then y is also going to be a. And what this translates to, well, if I know y is a, well, over here I have another y, right? Right over here, I have a y. So I could have written x is equal to 2y minus 1, but now I'm going to write x is equal to 2a minus 1. So now I have a way to write my system, 2a minus 1, comma a, for any value. You pick a number. If you wanted to come up with a solution, let's say a is 3. Well, if a is 3, then the first term would be 5, 3, 3. And if you don't believe me, test 5, 3, 3 in the original problem. It'll be a solution to all three equations. And you could pick any value for a. I picked 3 there. You could have picked 7 and done 13, 7, 7. That would also be a solution to all equations. All right, this is a short video. We are going to pick up with partial fraction decomposition in class next time I see you.